Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Finland. I'm a theoretical physicist and I specialize in cosmology. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool things happening inside the universe. I love talking about science and I love jumping here on Restream, on YouTube, on Twitter, wherever you're watching me from, to chat about all of the cool things happening in space, in the universe, in physics in general. It's great fun. I just love chatting to cool people about science. I mean, that's what we do this for, right? So hello, David Dunn. Hello, Wilfred Paul, joining over from YouTube. Great to see you both. Always nice to see the regulars coming back every week. Almost 7 years into Cup of Cosmology and you're all still coming back every week. I love to see it. Love to see everyone coming here. Hey, David, I am doing well. Thank you for asking. So last week there wasn't an episode of of Cup of Cosmology because I was on a break. It was a lovely break. Had a nice getaway, saw some really amazing sceneries, had some great food. Just had a really nice break last weekend. And then this week at work has been surprisingly intense, given that I took Monday off. It's been a surprisingly intense week, but it's good. Everything's going well here. I'm happy, doing well. So recovered from my break and really getting ready to push on a few things with work now. So doing well. Hey James, great to see you as well. Also, James is here from the early days, from the Periscope days, I believe. Been following me for 6 years now. Always great to see you. So yeah, I study the universe and all of the cool things well, not all of the cool things happening, but I study some cool things that happen inside the universe. And I love being a scientist, mainly because it lets me chat to really, really cool people about really fun topics. It's the most cool thing about the job. It's going up to random people who work on similar topics and discovering something new about science that I didn't know before. And I love sharing that with everyone and just chatting to everyone about space, about science, about everything. So this is what Cup of Cosmology is for. It's a place to ask all your questions about the universe, about science, about academia, if you want to get me to rant, and about all of the cool things we do. So Wilfred Paul asking, what are we talking about today? I actually came completely unprepared today, no topic. If anyone wants to propose a topic, let's go. We can improvise this. So I don't have a topic today, so I'm counting on people asking questions. If not, if people don't have questions, I'm going to ramble about my favorite things in the universe, which is always fun. So this is a place to ask any questions you have. As always, there are no stupid questions. Anything you want to know, this is the place to ask. And this is a judgment-free zone. There are no stupid questions, so you can just ask away and we will go from there. If there are not questions, I will talk about random topics that I find interesting. Also works. As always, if you like Cup of Cosmology, I would appreciate if you click the like button on the video if you're watching on YouTube or on Twitter. Subscribe if you haven't already to the YouTube channel. Leave a comment down below. All of this increases my engagement and somehow gets more followers to come in. I'm still rebuilding the audience after HAPS closed down recently and gutted my following. So any help in promoting the show and getting the word out there is always appreciated, because we definitely need to get more people coming in. So yeah, there is some exciting news coming up in 9 days. We will get the first images from the Just Wonderful Space Telescope, from JWST. This is the amazing telescope that launched on Christmas Day last year. It's considered by many to be the successor to the Hubble Space Telescope, even though Hubble is still working. It's an infrared telescope. It's going to look further back in space than we've been able to see with any of our normal other telescopes, with any of our other visible range telescopes. And it's going to produce some really, really cool images, some cool science. And the first images are expected on July 12th, which is 9 days from now. So that's definitely something to be very, very excited about, because from everything I've heard, the images are going to be amazing. Hey, David Howden, great to see you. Entomological matters kept you away. That's perfectly fine. The bugs come first. But great to have you here, as always, David Howden. All the Davids here now. Great to have you all here. I say all, both of you. So, yeah, we're expecting the first images from the Just Wonderful Space Telescope on the 12th of July, so in 9 days. The people who have already seen them, I have not seen them, obviously, but the people who processed the images, who did the cleaning, who have already seen them, have said that they are spectacular, that we should really have high expectations for these images, that they're going to be really, really amazing. So I'm super excited to see these first images. We'll get them in 9 days now. Yeah, it will be really cool to actually see these images. Then I'll have to complain again about the name of the telescope. But apart from that, it's going to be really cool to actually get these images after so many years of hype about this telescope and the launch and everything that's gone into it. To actually see the first images, and we've already seen, some stars that they've released as the alignment, but this is going to be the first science image, and we've been told that they've announced that it's going to be a deep field image. So much like the Hubble Space Telescope has taken these deep space images, the JWST is expected to do the same and show us galaxies that we've never been able to see before. So that will be really cool. I'm not sure what time of the day the images are going to be released. I think there's going to be a press conference. They always do press conferences, good PR. So there will probably be a press conference and then the image will be released. So I'm not yet sure on the timing, but that's definitely something to look out for. Definitely a cool thing to be aware of. So yeah, that's an exciting thing that's happening currently. Otherwise, I've honestly been a bit disconnected from space news lately because I took a break and just really tried to break away from everything, even though my mind was thinking about grants and stuff. I did take a break away from stuff. And this last week at work has been ridiculous. Just so many things going on, which surprised me the first week back from the break. But it's been a good week. But overall, it just means I haven't been keeping up to date with any science news. So I know there are the images coming, but if there were any major scientific announcements this week, I probably would have heard major ones. But I don't think there's too much big and new happening, other than a couple of conferences coming up, which I'm super excited for. So there's a big conference ongoing that actually starts tomorrow, which is a Cosmology from Home conference. Last year, I was a speaker at the Cosmology from Home conference, and we also the organizers set up 6 outreach events where I participated in all 6 of them. So we did 6 live streams as part of the Cosmology from Home conference last year in the space of 2 weeks. Now, I haven't heard of anything being planned this year, but it wouldn't surprise me if there's some conference outreach events. So if anyone here remembers the ones from last year, if not, you should go check them out. You can find Cosmology from Home on YouTube and find the outreach events. But those were really, really cool. So I'm hoping there will be some outreach again in the coming 2 weeks. Now, I probably won't be participating in all of them or any of them, I don't know. But I do expect that there will be some cool outreach events taking place in the context of the conference in the next couple of weeks. So that will be nice. So definitely stay tuned for that. Obviously, as soon as I get any info on that, I will share it with everyone as well. But that's going to be fun. And I actually have like a whole month of conferences now, which is crazy. So there's this Cosmology from Home that's taking place for 2 weeks. Then I'm in a conference in Vienna, an actual in-person conference, which is scary. And I'm going to be testing and wearing my mask every day. And then I go directly to another conference in Italy. So it's going to be a busy month for me. But I hope to do conference streams. Like I hope to do a stream both from Vienna and from Italy. We'll see. We'll see which conference members I can trick into joining me on the live streams. But I will try to bring you news from the conference because it's always fun to just show everyone what actually takes place at a scientific conference. So that will be fun. So I see it's quite a quiet day. I don't have a topic prepared. I see there are not too many questions. As always, this is a place where you can ask me any questions, anything you want to know about the universe, about space, about time, about black holes, about dark matter, anything you want to know. This is the place to ask. I might not have all of the answers, but I will do my best to try to answer any questions people do have. If there are no questions, I get to talk about my favorite things, which inevitably is going to lead us to the CMB, but let's see if we can do other topics as well, because I did a whole stream about the CMB very, very recently. And I've realized we're 10 minutes in and I already feel like I'm losing my voice. This is not getting off to a good start. I think what doesn't help is the heat wave that we've had for the last 10 days here. It is still 29 degrees outside, which is way too hot for Helsinki, and I am melting and not doing well in the heat, which makes me inherently tired, but doesn't matter. Tomorrow, Tuesday, I believe, heat wave should be over, and then I'll be happier. Okay, so at the beginning I said that I study cosmology, which means I study some of the fun things happening inside the universe, and that is pretty vague. So what do I work on? What do I do with my life other than, shout at computers and get computers to do stuff for me? So we know that the universe has three main components. Everything you see, everything you're accustomed to, everything from the stars you see in the night sky to me, to my tea mug, all of this is normal matter. Now, normal matter only accounts for 5% of the energy budget of the observable universe. There's another 25% that is in the form of dark matter. Now, dark matter is this weird type of matter that can interact via the gravitational force, but it doesn't interact via the electromagnetic force. This means it does not emit light, it does not absorb light, it does not reflect light. As far as light is concerned, dark matter is not there, which makes it very difficult to study something that is essentially invisible. So I see the chance here for the CMB. Yeah, we will get to the CMB. July 12th, so the images are going to be released at 2:30 GMT, which I believe means that it is 4:30 my time. So thank you for that, David. 4:30 my time on July the 12th. I believe I will be in a conference event, but I might skip the conference event because if there's a press conference for those images, that's more important. Okay, so 5% normal matter, 25% dark matter, and the remaining 70% is in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing everything outwards, and that's pretty much all we know about dark energy. It's there, it accounts for 70%, it's pushing things outwards. It's a mystery. We have no idea what it does. Well, we know what it does, we have no idea what it is. Now, most of what I've done up till now is studying this 25%, which is in the form of dark matter. Now, dark matter is difficult to study because it cannot be seen. So part of the things that I've been asking myself for the last 6, 7, 8, God, I have no idea how many years now. So let's count. I started my master's in 2014. So that is 8 years now. Oh, okay, so for the last 7 years or 6 years, let's count since I started my PhD, for the last 6 years, I've basically been asking myself, how can we study dark matter when we cannot see it? How do we study something that is basically invisible? And yeah, I wrote a whole PhD thesis trying to figure out how to study dark matter when we cannot see dark matter. So that's pretty fun. So I'm basically a dark matter person, but that means that in order to answer these questions, we'll use a lot of different cosmological observables. So this led me to the CMB and to Lyman alpha data, which I've done streams about. But yeah, one of the biggest questions I've tried to ask is, how do we study dark matter? And it's a pretty cool question. So I did see a comment from James here. I always have questions, but was walking down 2nd Avenue to cafe. Nice, enjoy your coffee or whatever drink you're getting at a cafe. Crazy question. I'm glad you didn't say stupid question, else I would have had to correct you there. Crazy question. I love crazy questions. You understand E equals mc squared, but don't understand c squared equals E divided by mc using math division. So I'm not completely sure I get what you mean here. So E equals mc squared is Einstein's typical equation. The energy that the energy that a particle or system contains at rest is equal to the mass of the system times the speed of light squared. Now, it's important to notice that this is the rest energy. So when an object is at rest, as soon as you have an object that is moving, this equation becomes a bit more complicated because then it's actually mc squared plus the momentum squared times c squared. So then you actually have an additional term as well. C squared, c to the 4th. Yes, then you actually have an additional term to account for the motion of the particle. So E equals mc squared is just the case where you have a particle at rest. Now, it is often the case where, for an example, we will express the energy of a particle in terms of this formula. So when we give the mass of a particle, for an example, sorry, not its energy, when we give the mass of a particle, we might give it in electron volts over c squared. Now, what this means is that we just move the equation around slightly so that we can express things in terms of energy, because it's just a bit easier to understand. Because when dealing with particles, if you start talking about the mass, it's what units do we use? So we often just express the mass in terms of energy divided by c squared. But the good thing about an equation is you can move it around however you like. So basically, you just multiply both sides by the same thing or divide both sides by the same thing. It's like if I tell you you have, x equal 2, and I tell you on both sides of this equation you can multiply by 3, it's still going to be the same. 3x is going to be equal to 6. So here we're just moving things around. So you can go from E equals mc squared to mathematically saying that c squared is equal to energy divided by mass. I do see you said there c squared is equal to E divided by mc, and I think there's an extra c squared there, an extra c there. But I'm not completely sure what your question was there, so I just rambled about the equation. So I probably didn't answer your question, so feel free to ask that again if my answer didn't make any sense. But yeah, you have the energy equals mass times the speed of light squared, and you can move this around a bit. I've answered this before, but you've forgotten. No worries, David. I'm always happy to re-answer questions. What does at rest mean for rest masses? I understand there is no absolute frame of reference against which to rest. Oh, I love this question. Now it's getting complicated. So usually what we do is we put ourselves. You can consider some rest frame for what you're doing. Let's see how we can. It is a great question. It's basically if you were in a frame of reference where you could consider the particle to not be moving. For an example, if you're traveling with the particle itself, then you will not see any motion of the particle because your rest frame is moving with the particle. So this is absolutely right. For Einstein's general relativity, or for Einstein's special relativity even, we know that there is no absolute frame of reference. You can choose any frame of reference and your measurements are going to depend on where you're doing your measurements from. But one way we can think about this is imagine you're on a train that's moving, right? And you want to, and then you throw a pencil. You throw a pencil up and down, you throw a tennis ball on a train that's moving. Now, if you calculate the motion of the tennis ball, you only need to consider its motion relative to you. And as you are moving with the train, you only consider its motion relative to the train. But if somebody is outside on the platform and sees your train zipping past and the tennis ball going up and down, they have to consider two motions, the motion of the train and the motion of the tennis ball. So depending on who's asking the question of how fast is the tennis ball moving, or what is the tennis ball doing, depending on where you're asking this question from, you will get different answers. This is the idea that there is no preferred frame of reference. Every answer is equally valid. It's just from a different frame of reference. Now, if you imagine that you're moving with a particle, so if you have a particle traveling close to the speed of light and you were to move with that particle, then you can kind of neglect the motion of the particle itself. But that particle will still have intrinsic energy, and this is because of its intrinsic mass. Unless it's a particle moving at the speed of light, and then it might not have mass. But if you have a particle, if you're moving in the rest frame of the particle, then you can consider the rest mass. Now, usually we consider what we call the lab frame. So if you have particle collisions, you can account for a frame of reference where all of the motion is well understood. And then you can really account for this rest mass. So the rest mass is basically, if you could stop a particle perfectly and see it, it would still have an amount of intrinsic energy and mass. Now, of course, usually you are not going to be in the rest frame of the particle. But if you were in the frame where you can ignore any motion of the particle, you are still left with this amount of energy. So one way to think of it is any other contributions to the energy coming from movement, you can kind of change by changing your frame of reference. But it will always have its intrinsic mass, which is what is in Einstein's E equals mc squared. It's quite fun because, E equals mc squared is a very famous equation. Everyone knows it. And when I started my undergrad, one of the first things I was taught is that that's wrong, because it should actually be E sub 0 is equal to m sub 0 c squared, because it's the sub 0 indicates that you are in the rest frame. So that is absolutely a great question, that there is no absolute frame of reference against which to rest. That is an excellent point, David. I hope that clarified the answer. I hope my answer clarified that or answered your question. If not, as always, please do ask again, and then we can try to answer it again. But I hope that somewhat offered a bit of clarification. I have also noticed there is a very slight lag in the comments on YouTube being sent into Restream, where I'm streaming from, as you can tell by the logo up here. So if I do have a delay in answering your questions, it's partly because I'm slow with questions sometimes, and it's partly because there is a slight lag. You think you've understood that? Great. That's good. It is a very, very cool question to ask, and it is a good question to ask because there are no preferred frames of reference. So when we talk about rest mass, it gets a bit complicated. on a completely off tangent comment here. I got my first tattoo yesterday, which I'm really happy with. And like 10 minutes before I was set to start this stream, it started really itching. So if at any point I look distracted, it's because I'm making a mental effort to not scratch my tattoo. So just slight aside comment there, because that's where my mind is currently. Okay, so I was saying just now that mostly I've been working on dark matter and asking this question of how can we study something that is invisible? And there are actually several different ways we can go about studying dark matter. Did I get a CMB tattoo? I did not get the CMB tattooed yet. Emphasis on the yet. But no, I did not get a science tattoo. It's not even a geeky tattoo. It's just a tattoo that's in memory of my dad. So it's not a CMB tattoo. Can we ever observe something at rest, or would that mean we knew its velocity perfectly, so its location must be unknown? Haha. Excellent question, David, hitting me with the tough questions. So I see if I don't prepare a topic, then we go into quantum physics, which is always fun and difficult. Quantum mechanics, fun and difficult topics. CMB tattoo would be very painful. Yeah, if I get the full CMB, that would be difficult. But getting the CMB spectral decomposition, like the acoustic peaks of the CMB, that would be relatively straightforward tattoo to get. Let's not go down there and start thinking of my next tattoo when I've only just got my first one, shall we? So, Heisenberg's uncertainty principle tells us that you cannot simultaneously measure with incredible precision the location and the momentum of an object. So I can either tell you a particle is here, or I can tell you how fast it's moving. The reason for this is that to make these measurements, you are going to slightly impact the system. Because in quantum mechanics, systems are impacted by the observations you make. And we know this is true. So if you have a particle that is traveling, you can either say it is exactly here, or you can say it has this momentum, but you cannot say both. And the more precisely you know one of these, the less precisely you know the other. So the more accurately you get its position, the less you know about its velocity, and vice versa. So if you measure its velocity really well, then its position becomes very uncertain. This is Heisenberg's uncertainty principle, and it does indeed mean that measuring something that is perfectly at rest is quite hard, because then it means we cannot really know its velocity and vice versa. So we do have Heisenberg's uncertainty principle. Now, of course, this only applies to particles. Obviously, I can say my tea mug is at rest relative to me on the table, and I can tell you it's not moving relative to me. I hope it's not moving by itself, because these are macroscopic objects, and then you no longer need to concern yourself with Heisenberg's uncertainty principle. But when you go down to the quantum scales, you do have this issue, that you can either measure one property or the other. And it's not just with the position and the velocity. There are other properties that are also kind of together, that you can either measure one or the other. So observing a particle at rest so precisely that you can say this particle is perfectly at rest would then be an issue in terms of the uncertainty principle. So I do see people saying hello to Ange, but I don't see Ange in the comments. So hi, Ange, great to see you here. I'm not actually seeing any of your comments, but seeing that people, there it is there. Okay. The link from Twitter goes to a video where the chat isn't working. Yeah, this is a Twitter thing. So Twitter used to allow comments to go in both directions. Twitter no longer allows that. So Twitter doesn't allow comments anymore. When Twitter brought out the Periscope interface and incorporated the Periscope comments, then Twitter decided to shut down Periscope for reasons that I will never fully understand, business decision, and then they stopped the comments. So if you want to join the discussion, you have to do it on YouTube, I'm afraid. I do think if you reply to the tweet where the video is on Twitter, the comments should come through. But generally, Twitter now is useful for viewing videos, but not for joining the conversation. So if you want to join the conversation, the best place to do that is unfortunately over on the YouTube channel, until I figure out the better place to move it. But YouTube, is not going anywhere. Twitch is just really not my thing. I tried Twitch, didn't click. I didn't click with Twitch. So yeah, the best way to join the conversation is over on the YouTube channel. where pretty much everyone these days has a Google account or a YouTube account or both. They're connected now. So hopefully most of you can join in on the YouTube channel. But yeah, on Twitter, it is an issue that comments don't appear to work on Twitter. But don't worry, you didn't miss much, just me talking about a potential second tattoo involving a CMB. But we'll see. Still getting with the first one. So yeah, you can make a lot of jokes about the Heisenberg uncertainty principle. There's the very typical one that Heisenberg is driving in his car and is stopped by the police, and the police says to Heisenberg, "Do you have any idea how fast you were going?" And Heisenberg says, "No, but I know exactly where I am." And of course, that only works because Heisenberg likes his white men and it can be stopped by police. But let's not go on that rant, shall we? But yeah, it is a very, very interesting question. And I love that if I don't prepare a topic, you hit me with tough questions about Heisenberg uncertainty principle. I feel like I definitely need to brush up on that, which I will hopefully do soon, because I'm going to be tutoring for a quantum mechanics course, quantum physics course next year. So I will definitely be brushing up on those topics. Yeah, so some people find that Twitch works. I think my problem with Twitch is I was always using Twitch from somewhere else. So I was using Twitch from Restream or Twitch from Haps. And I think to really get into Twitch, you have to be Twitch native, kind of using it directly on the platform. It's also the thing that I just don't use Twitch to watch other people, and I still don't really understand what all of the buttons do, and there's a lot of stuff, and it feels like you really need to get into the whole Twitch lingo, and I'm just not there. YouTube's easy, like, subscribe. These are options we're all used to and familiar with. So yeah, I just found that Twitch didn't really work for me, but it does work for a lot of people. David Dunn is over on Twitch. There's a lot of cool people on Twitch. Okay, so before the next quantum physics question comes in, please do keep them coming. I love these questions, and I really do like the quantum physics questions as well. It's always fun to go off on these topics as well. So I was asking the question before of how do we go about studying dark matter when dark matter is invisible? And of course, there are several different ways we can go about doing this. And the biggest one is asking the question of what is dark matter doing to other things? So I mentioned before that dark matter interacts via the gravitational force. So there are four forces that we know of in the universe. There is the electromagnetic force, electricity, magnetism. This is what we're used to. You have an electric current, you have a magnet. We have the gravitational force. We're also pretty familiar with this one. I drop a pen, it falls down. We stay in orbit around the sun, gravity. Then we have two other forces, which are the strong nuclear force and the weak nuclear force. The strong nuclear force is responsible for holding everything together. The weak nuclear force is responsible for radioactive decay. Now, to the best of our knowledge, dark matter has gravitational interactions, does not have strong interactions, it does not have electromagnetic interactions, and it might have very weak interactions. So then the easiest way we can go about studying dark matter is by looking at how it affects other things in the universe. And in fact, this comes back to how we know that dark matter exists. So because dark matter has mass, it will distort the gravitational field, and it will therefore cause a gravitational effect. So by looking at how stars move around galaxies, we can study dark matter. By looking at the way light is distorted when it comes at us from distant objects, we can study dark matter. By looking at how galaxies crash together and how everything moves around, we can study dark matter. And one of the easiest ways we have to study dark matter is, of course, using my favorite thing, the CMB, the cosmic microwave background radiation. This is the oldest light we have in any direction we look in the universe. This is the afterglow of the Big Bang itself. This was produced, and I know my regulars have heard me do this hundreds of times, doesn't matter, and I can never do this without smiling because the CMB is amazing. So, in the early universe, you had photons, electrons. These were all buzzing around, bumping into each other. It couldn't really move much. The photons were bumping into the protons were bumping into the electrons, the photons here being particles of light. As the universe cooled down, the protons and the electrons could combine together to form neutral hydrogen. At this point, the photons could no longer bump into the other particles as much, so they started traveling freely. These photons are still traveling freely in the universe, and today they make up the CMB, the cosmic microwave background radiation. So this is the afterglow of the Big Bang itself. It's the light that was produced 380,000 years after the Big Bang. So about 13.8 billion years ago from our perspective. Pretty impressive. And you'll notice here that while this just looks like blue spots and orange spots, what this is the overall temperature of these background photons. Now, these background photons have approximately the same temperature. Everything is at approximately 2.73 degrees Kelvin, which is minus 270 degrees Celsius, and I believe minus 400 and something degrees Fahrenheit. So it has this almost perfect temperature, but there are tiny, tiny differences of the order of 10 to the minus 5. This means that you have some photons that are 0.00001 degree hotter or 0.00001 degree colder. You have these slightly hotter photons and colder photons, slightly more and less energetic photons. Now, the reason you have more energy in some and less energy in others is because at the time when the CMB was formed, apart from the photons and the electrons and the protons, we also had dark matter. Now, dark matter was clustering together gravitationally. It was pulling things towards it. So if you have a cloud of dark matter and things start falling into it gravitationally, you're going to end up with more protons, more electrons, more photons in the regions where you have more dark matter. So then you form what we call a gravitational potential. You have an area where you can imagine objects bending space-time. You have this well. These objects are dark matter and all of the particles that are gravitationally bound to the dark matter. When the protons and the electrons combined together and the photons broke away, some of these photons were in the valleys where there were these potential wells. Others were at the top. So the photons that were in these valleys, these dips, first had to climb out of the well in order to travel through the universe, and they already lost some energy doing this. Now this leads to some regions in the CMB that are hotter, some that are colder. The photons that had to climb out of these overdense regions lost more energy, so they're slightly colder and bluer on the map today. So by looking at how many orange and blue photons, how many hot spots and cold spots we have, and more importantly, how big the hot spots and cold spots are, we can understand what dark matter and dark energy and everything else was doing 380,000 years after the Big Bang. So CMB is amazing. It allows us to understand the age of the universe, the size of the universe, the shape of the universe, the components of the universe. It allows us to say there's 70% dark energy, there's 25% dark matter, there's 5% normal matter. It tells us a bit about inflation, this period of exponential expansion in the early universe. It also tells us at which time the first stars potentially began to form. So there's a lot of information hidden in this pretty little map that you can see down here. And it helps us study dark matter. So a lot of what I've been asking myself over the last 6-7 years, however long we want to consider that I've been a scientist for, has been asking myself, how can we use the CMB to study dark matter? But not just the CMB, how can we use hydrogen clouds in the universe to study dark matter? But the key theme throughout most of my papers has actually been dark matter. Okay, I'll come back to this. I'm just filling the gaps here with random stuff like CMB, dark matter. There is more or less a thread linking everything, but there was a question here from James. Do we know if the radius of the universe is equal in all directions? Is it possible for one side to expand faster than others? Now, this is an excellent question, and there's a lot to unpack in this question. Now, the first point is, what do we mean by the radius of the universe? And this gets complicated, because the universe, to the best of our knowledge, is infinite. It is infinitely big in every possible direction, which means you can't really define a radius. However, we can then talk about the observable universe. Now, we know that the age of the universe is finite. The universe has been around for about 14 billion years. And we know that light can only travel at a specific speed. Nothing can travel faster than light in a vacuum. This means that there's only a limited patch of the universe that has been able to hypothetically send us information. This doesn't necessarily mean this is the patch we have actually been able to see, given our technological limitations. But this is the patch that hypothetically we would be able to see if we had unlimited seeing power. And it is limited by the speed at which light is propagating. This means that you can actually define this observable universe which is centered around you, which has a radius of about 46 billion light years. Now, this might seem strange because we know the universe is about 14 billion years old. So you might say, okay, light has traveled 14 billion years, so the radius might be 14 billion years. But the universe is undergoing accelerated expansion. Things in the universe are moving away from us faster than they have been in the past. This expansion of the universe means that if a galaxy emitted light to us when this galaxy was 2 billion light years away, by the time the light reaches us, this galaxy is even further away. So even though it's only taken 2 billion years for the light to reach us, we're actually seeing light from a galaxy that is more than 2 billion light years away because of the expansion rate of the universe. So the observable universe has a radius of about 46 billion light years. And this is in every direction the same, because by construction here, we're not limited by the actual physical size of the universe, but by how much of the universe could have sent us information, given the age of the universe and the finite speed of travel of light. So we can say that the observable universe has the same radius in every direction by construction. However, talking about anything beyond that is not something we can actually do, because we are always, by definition, we are always limited to whatever is inside our observable universe. And what we say then is we don't think our observable universe is in any way privileged or special or different. So we can assume that our observable universe is a fair reflection of the universe in general. So anytime we talk about the universe, we're basing ourselves on actually what we've seen in our observable universe, and we're extrapolating outwards. So that makes it very hard to talk about a radius of the actual universe, because the universe is infinite. And if you talk about radius, you start trying to put a size on the universe, but the universe is everything in existence. So then, to your second question there, James, is it possible for one side to expand faster than the others? Now, this comes to a very interesting question of, could you have regions of the universe that are expanding at a different rate? And the answer there is potentially yes, and this would be really, really cool. So we know that the universe is currently undergoing accelerated expansion. It is expanding, and this expansion is faster than it was in the past. We also have a bit of an issue trying to pinpoint exactly the expansion rate of the universe. Depending on how we ask the question of how fast is the universe expanding, or at what rate is the universe expanding, depending how we try to answer this question, we get slightly different answers. Very slightly different. They're in the right general area. They're in very good agreement, but they're not perfect. And one idea that some people have come up with is that there could be patches of the universe that are expanding differently. In regions where you have more matter, for an example, you could potentially have a back reaction effect where the matter slows down, and that has a knock-on effect because you have more gravitational force. And you could have regions where you have no matter, and therefore dark energy that isn't competing against anything. There are ideas where you could have this uneven expansion rate of the universe. Currently, we haven't been able to find any clear evidence for uneven expansion rates. It would be pretty cool because it might help us understand why we're getting very slightly different results when we ask this question. But it is not completely clear. So it is a great question to ask. So to recap, your first question, do we know the radius of the universe? We know the radius of the observable universe. We cannot say anything about the radius of the universe in general. By construction, the radius of the observable universe is going to be the same in every direction, because here we're only limited by the speed of light and the age of the universe, both of which are well-known quantities. Is it possible for one patch of the universe to expand faster than others? Potentially, yes. There's no reason why mathematically you couldn't do this. It's not something we've been able to confirm yet, but it's something that some people are looking into because it might help us explain an issue that we have when we do different measurements. So those are all great questions, James, and I hope that with that answer we covered all of your questions there. If not, as always, feel free to ask again and we can go through the questions again. I wonder sometimes why I wear headphones in my streams. When I have guests, it makes sense because then we don't have echo. But when it's just me, I always wonder why I'm wearing the headphones, and it's just out of habit. Anyway, another just random tangent there, just because I noticed my headphones were bothering me again. Okay, so I meant very cool. Yes, awesome. Thank you for the questions, James. As always, keep them coming. I love the questions. This is what we're here for, is to answer these fun questions. So I mentioned before that most of what I've done up till now is working on dark matter. Now, I've also branched out. I've had a few papers where I'm looking at the expansion rate of the universe and other cosmological tensions. I've looked at fun things like spectral distortions, which are a whole other property of the CMB that it is basically a treasure trove of information that we haven't yet exploited, which is really, really cool. I've also worked on neutrinos, I've worked a bit on inflation, but the main theme behind a lot of my work has always been dark matter. But now I actually recently changed topic when I moved to Helsinki. Now I'm still working on dark matter and still doing some projects there, but I've also shifted to a different focus now, which are gravitational waves, which, as everyone knows here on my streams, is another one of my core list topics. Gravitational waves, amazing, amazing stuff to work on. And gravitational waves are ripples in space-time. So if you imagine when you go through a swimming pool, you produce ripples. Now, things in the universe can also do this and produce ripples of space-time themselves. So gravitational waves are ripples in space-time. They are ripples of gravity. So they are basically tiny, tiny, tiny waves that carry a gravitational force with them. And they are produced by some of the most cataclysmic events in the universe. So if you have two black holes smashing together, this is going to produce gravitational waves. Sorry. If you have neutron stars smashing together, or neutron stars and black holes smashing together, this is going to produce gravitational waves. But also more dramatic things like supermassive black holes at the center of galaxies eating up other things like neutron stars. This would produce gravitational waves. If you have two supermassive black holes smashing together, you get gravitational waves. But also in the very, very early universe, we believe there was a period known as inflation. Now, inflation is a time at which the universe grows exponentially. You have this exponential expansion, which basically means the universe is growing ridiculously, a ridiculous amount in every direction. It's just like this massive exponential expansion in the early universe. And this was such a dramatic event that it could actually have left ripples in the fabric of space-time in the form of a background radiation of gravitational waves, in the same way that we have the background light, which we call the CMB. So in the same way that we have this background photon radiation everywhere we look in the universe, there could be a background gravitational wave signal, like gravitational waves hidden in the background of the universe. And not only can these be caused by inflation, but by any other dramatic thing that happened in the early universe. So there are some things that we know might have happened in the early universe, and one of them is called phase transitions. Now, phase transition is something that we experience in our day-to-day life. If you freeze water when it goes from liquid to solid, that's a phase transition. If you have a shower and you get condensation everywhere when you're turning this water into vapor, into this kind of gas state, there you have a phase transition. And the universe also could have had phase transitions when it was really, really in its infancy, like in the first picoseconds, in the first fraction of a second of the early universe, there could have been phase transitions. And these phase transitions would happen as little bubbles. So it would start happening here and over here, and maybe up here, and maybe up here. So you have these bubbles with the new phase, which are gradually overtaking the old phase. So you have to imagine the universe is in one phase, and suddenly these bubbles of the new phase start appearing. Now, if these bubbles collide, which they would do because they're gradually growing to take over the old phase, as they grow, they will collide, and the collision of these bubbles could actually produce gravitational waves, which again would be hidden in this background gravitational wave signal everywhere in the universe. And this is mind-blowing to think about, that we could have these really early universe processes, like we're talking about the first picosecond of the universe. And you could have these phase transitions, these little bubbles appearing, crashing together and producing gravitational waves that we might be able to detect someday in the future by sending laser mission to space. We're basically going to send 3 spacecrafts to space that are going to chase after the Earth and bounce a laser back and forth between them. And we're going to use this to try to look for gravitational waves coming from supermassive black holes smashing together, coming from neutron stars falling into supermassive black holes, coming from binary systems within our own galaxy, and potentially coming from these very, very early universe events. And this is incredible to think about. And currently, this is actually what I'm working on. I'm trying to ask the question of, could these bubbles produce gravitational waves? Of course, a lot of people have already done this. A lot of people much smarter than I have already done this. But is this something that the future mission LISA can detect, this space triangle? And if LISA detects something, what does that tell us about the phase transition? Can we do the process backwards? So if LISA has a detection, how do we then unwind it and understand the early universe? And that's what I'm working on today. And, you know, the CMB is always going to be my first love in the universe. And dark matter is a topic that I'm really passionate about. But these gravitational waves from this early universe stuff, it's a really cool thing to think about. And I get paid to think about these things now, which is really cool. So this was a whole tangent. The whole story today is just what I work on. The conclusion is I work on fun stuff. And I noticed I missed 2 questions here because I was just talking about phase transitions. I think you mentioned in a previous show that Milky Way could be in a void. Did I hear this right? Yes, it could be. So there is this idea that we could have a local void. So we know that the Milky Way, our galaxy, is part of a local group of galaxies which are embedded in a local cluster, the Virgo cluster, which is then embedded in an arm of the cosmic web, which we call Laniakea. But it could be that there's some void around us. This is something that people propose to address this problem of the expansion rate of the universe. Could we be in a local void? So this means we're asking the question, could our patch of the universe just have slightly fewer galaxies than other patches of the universe? We haven't yet found clear evidence saying this, but it is something that people are asking. Could the Milky Way be in a void? Again, currently the answer is we haven't found any evidence to say so, but it might be. So that is indeed something that some people are looking at to try to solve the expansion rate, of the discrepancy we have in the expansion rate of the universe. So really, really nice question from David here. Talking about bubbles makes you wonder if there needs to be something for the phase change to form around, to nucleate around, like bubbles in liquid need. So I know we have discussed this in previous streams because I've had 2 people who've worked on this for a lot longer than I have joined me on the streams, or 3 people by now joining me on the streams to discuss this. Now, my answer is not necessarily going to be correct here, but the idea is you don't necessarily need something for them to form around. If you have the right conditions for this phase to appear, the idea is it can start randomly appearing as these bubbles nucleate. So you have the bubble nucleation, and the initial configuration of this might be random, and then you have the bubbles colliding. So I don't believe you need something around which the bubbles nucleate, just the bubbles themselves just nucleate when the conditions of the universe, or the conditions necessary for this new phase are right. But this is something that, as I said, I only started working on recently, and I'm still figuring out the finer details like that question. So perhaps take my answer with just a pinch of salt. I do plan on getting an expert on this topic on at some point, we'll see. But we have already had 2 or 3 people who've worked on bubbles on the show. So there was an episode where we talked about how we produce the bubbles. There was one where we talked about how we study them in a computer. And there was one where we talked about how we can use holography to study bubbles. Haha, cool. And I do want to do more streams about this topic because it is super fun to think about. And also ridiculously confusing to think about these bubbles in the early universe that somehow collide together and form gravitational waves. And yeah, it's super cool to think about, but also I still find it completely mind-blowing. I think it's not only mind-blowing that this is a concept that might actually be measurable, but that we know how to study this, that we can do computer simulations that can actually predict what these bubbles are going to do. We can run a code that will show these pretty simulations. Like, look, here's a bubble nucleating and expanding and crashing into other things. And then we can match this to like, okay, if these bubbles existed, they would produce this gravitational wave signal. LISA could potentially measure this. The fact that not only can we ask these questions, but that we know how to mathematically describe this and how to get a computer to simulate this for us, it's ridiculously mind-blowing when you think about it. And we're talking about something that happens in the first millionth of a second after the Big Bang. So in the first millionth of a second of the early universe, after inflation, of course, we don't know how long inflation lasted, but at some point after inflation, in the first, when inflation ends, we consider the start of the universe. And then in this first millionth of a second, you could have had these bubbles. And this is something that potentially could be measured 14 billion years later by a space triangle sending lasers back and forth. It's mind-blowing. It's if someone had told me that 10 years ago, I would have said that sounds like some black magic to me. I'm still not completely convinced it's not black magic, but it is cool black magic that I get to work on. Then that makes it interesting. And of course, magic is just what we call something that we haven't fully understood yet. So yeah, when I don't understand the code, it's black magic. Once I've understood it, it's science. That's how things work. I see comments aren't completely coming through. At least I see an empty comment there. I guess the comment itself will come through. You can't get enough of bubbles. I agree. I do agree there. I'm also very slightly amused that for most of my life I supported a football team whose anthem is "We're forever blowing bubbles," and now I literally work on cosmic bubbles. It just feels like this is always where I was headed. Just slight aside comment there that always amuses me. But yes, we can't get enough bubbles. I agree. There are plenty of people in my office working on this. And I do have a list of people who I plan on getting on my streams at some point, but we'll see when that happens. Obviously, no pressure, and that doesn't depend on me. But I will keep inviting people and see who else we can get. You weren't going to mention the West Ham connection. Yeah. It is quite funny, right? That after so many years of singing that anthem passionately with the football flags around me, I was a huge football fan for many years. And now here I am studying cosmic bubbles in the first picosecond of the universe. Yeah, fun twists and turns that life takes us to. So you've all had some cool questions, and my overarching tangent story here was I've worked on a lot of cool stuff. I used to work mainly on dark matter. Now I'm working on gravitational waves. They're both really, really cool topics. And I'm also currently at a very interesting point where I need to think about what I want to work on in the future because I'm writing grant proposals. Now, grant proposals is basically me asking funding agencies to give me money so that I can continue to have a job. It's fun. And, just in case anyone's worrying, my job is currently guaranteed right now for a while, at least for the next 2 years, 2.5 years. But I am writing grants, asking funding agencies to give me money so that I can continue doing my research. This is just part of the scientific life. And now is a cool time because now I actually can ask myself, what do I want to work on? If I'm writing a grant proposal and I get to choose what I work on in the future, what do I want to work on? And then there's a problem that I find everything so cool. It's like CMB, dark matter, gravitational waves, phase transitions, I will work on everything. So yeah, that's fun. And if anyone sees me stressed at any point this summer, it's because of grants applications. But yeah, it is fun and scary to ask the question of what do I actually want to work on. It feels like a big decision, even though, I've changed what I've worked on multiple times, and sometimes you find new fun, shiny things to chase after and to work on for a while. So it's also not a lifelong commitment, unlike getting a tattoo. I am indeed named after an alien from Star Trek, which is a great icebreaker. Because unsurprisingly, a lot of physicists are also big nerds. Like I know a lot of physicists who like Star Trek. And usually at conferences, you might not have good icebreakers. And it's a great icebreaker. It's like, hi, I'm Diana. I was named after an alien in Star Trek. Because a lot of people at that point are like, okay. So that is a great icebreaker. Cosmology recruitment should include get to travel the world. There's so many places to. Yeah, honestly, this is one of the nicest things about being in science and in academia, is that I do get to travel the world a lot. I have lived now I'm in my 6th country. I move around a lot for the job, and in non-pandemic times, in the before times, I did travel a lot to conferences, too much actually. Thinking about it, the carbon footprint of all the travel we do in academia is not great. And it has good and bad things, right? The traveling part is amazing. I've always had the travel bug. I've always loved traveling and visiting new cultures and getting to know new people. This is, to me, really, really cool and a great aspect of the job. But I'm also highly privileged. I can travel because I don't have people I need to take care of. I'm in a position where I can travel, where I can move country. But also expecting people to move country for their job every couple of years is not an ideal situation. So it goes both ways. I get to travel the world, and for me, that is an incredible privilege. But I'm lucky to be in the situation where I can just uproot my life again and move to my sixth country. Not everyone is in that situation. And, it's the thing that it's expected of PhDs, of postdocs, that we are going to travel, that we are going to change country at least once or twice. I was told the easiest way to kill your career is to stay in the same country for more than 5 years. Like, okay, what if I want to settle down? What if I want to buy a house? Which country do I do that in? So I get what you're saying here, James, that getting to travel the world is absolutely a privilege and a huge, nice thing in academia. It also has its bad sides. And also, as we move forward, the pandemic is not over, despite what a lot of people might think or might want to believe. Through the pandemic and going forward into the future, we also really need to ask ourselves, do we need to do so much traveling? Does it make sense to travel for 1 week to give a 20-minute conference? You have people flying in from all over the world. Is the carbon footprint justifiable in today's climate crisis? Is it meaningful? Does it make sense to get people to do this? And if we are going to do this, is it done in a fair way? Because currently, a lot of academia is based on this. Here comes the rant. A lot of academia is based on a reimbursement culture where we go to conferences, where we book hotels and travel, and then we come back and claim the money back. And for early career researchers, for early career researchers, this is a lot to ask people. To ask a PhD student on a limited stipend, go just pay for this conference, we'll reimburse you in a couple of months. It's discriminatory, it's ridiculous, and it needs to be stopped. Just that was a whole off topic tangent there, but it's something important to consider. So moving forward, we really do need to ask ourselves if we need to force people to travel to conferences. Personally, I think all conferences going forward should be hybrid. Not everyone thinks the pandemic is over, with reason. Not everyone is comfortable traveling. Not everyone is in a position to travel. I think hybrid conferences where you have in-person attendance and online attendance is absolutely the way to go. So that was just like, you got a whole couple of rants packed in one there. So traveling in academia is an amazing part of the job. I personally love it. I love going to conferences, but it's something that is a privilege, and it's something that should not be expected of students and a postdoc, and especially the whole thing of uprooting people's lives every couple of years and moving country. And it's a big thing to ask people. So it has pros and cons, both at the level of moving country and at the level of conferences and getting to go to these places. These conversations are definitely happening, and they need to happen more as to, how can we make conferences and this whole moving thing better for a lot of people. And these conversations are happening. But overall, I do agree that getting to travel so much, more than the travel, getting to meet people from so many different places, with so many different approaches to science, with so many different experiences and backgrounds, and hearing these fun having these fun conversations, this is one of the reasons I'm still in academia, because this makes it worthwhile for me. But yeah, being part of a graduate school was the travel to conferences, and it's fun, but also stressful. And then, I'm doing an online conference for the next 2 weeks, which I will only partially be attending just because I do not have the headspace to do 4 weeks back-to-back of conferences. And then I'm going to 2 in-person conferences, and I'm going to both of them back-to-back because they're not too far away, and then I can string them together and reduce my overall travel. And I'm doing a lot of it by train, which involves 1 day of 13 hours train travel and another day of 10 hours train travel. But then I minimize my flights. And I am looking forward to both of these conferences because I will get to see a lot of people I haven't seen in a long time and get to really network with some people that right now I really want to see again. It will be good. It will be good. Traveling to conferences is fun, but I will absolutely be masked and testing every day because this pandemic is not over. And going to conferences is a huge risk, and I go there fully aware of the risk and I'm going to try to minimize it. Have you seen the midnight sun yet? I have not. I have not yet been to the Arctic Circle. So last week I went 4 hours north of Helsinki. We basically didn't have any darkness. Like the sun was setting after 11 o'clock, and the sun was up again at 2:30 in the morning. So you don't really get darkness. You just kind of get this twilight. But I haven't been far enough north to actually see the midnight sun yet. I do plan on doing that at some point, but I haven't done that yet. But I have the problem that I need darkness to sleep. Midnight sun sounds spectacular, and only having 2-3 hours of twilight and no darkness is amazing. But also, then I don't sleep. Blackout curtains will only do so much for me. If I know the sun is up, I'm up. So yeah, my sleep schedule the last 4 months has been all over the place. But we've passed midsummer, days are getting shorter, which means winter is coming, and I, for one, cannot wait. I know most people enjoy summer. I'm all for everyone going out and enjoying the summer, but I'm counting down until winter's back because I am a winter person. Mainly because of the heat wave currently is really making me miss winter and the minus 10 degrees and snow that we had in December. And just like that, we've reached over an hour of the stream. So time flies. Time really does go quickly. I always find with my live streams, the first 10-20 minutes like slow, and then suddenly we're at 1 hour. It's like, okay, I've been rambling for an hour here. So thank you everyone for joining. This has been great fun, and thank you for the questions. As I said, I came completely unprepared today, no topic ready, just going to wing it. You had some great questions, which really helped move the conversation along. I got to ramble about some of my favorite topics. We covered CMB, dark matter, gravitational waves, phase transitions, all the fun things. And you even got me to rant a bit about academia at the end. I've been talking very fast. Yeah, that tends to happen. I haven't even had coffee today. I'm just hyped, just a bit hyper. So thank you everyone for joining. I will be online again next Sunday. I haven't yet figured out the topic. As always, if you have any topic requests, any proposals, anything you want to hear about, let me know. Maybe I'll have a guest, maybe not. I haven't had a guest in a while. I will be online next Sunday, same time as today. That's 7 p.m. Central European Summertime, 1 p.m. if you're on the East Coast, 10 a.m. if you're on the West Coast of the US. And please don't ask me more time zones. If you need a time zone converter, you can go to cupofcosmology.com. There you can see this in your own time zone, nice big time zone converter. Extra fast today, and I am sorry for that. I didn't notice I was speaking exceptionally fast, but that does happen sometimes, especially when I talk about the CMB. I know I get carried away there. So thank you everyone for joining. If you haven't done so already, please do subscribe to the YouTube channel. And please do spread the word of Cup of Cosmology, because this is how I grow the audience. Just I rely on you all going out and shouting about Cup of Cosmology from the rooftops. Maybe don't start knocking on people's doors like, have you heard of Cup of Cosmology? But if you want to, please go ahead. So I will be online again next Sunday, same time as today. And I hope in the meantime, you all stay safe and take care of each other.